All right. Thanks, Johannes. All right. Good morning or good afternoon, everyone. So the next 30 minutes, I try to sharing some of the work we have been working on to transition our compiler, Intel compiler technology, to the new generation of the Intel compiler based on the LVM infrastructure for Intel's CPU and accelerators. So we already have some public beta release, which we call the Intel One API. One API is the Intel brand of the toolchain. So basically, we have this HPC toolkit, which includes a DPC++ compiler and the Intel C++ OpenP offloading compiler for the HPC. All right. So agenda for today's talk, essentially, let's look at the landscape of our software toolchain for the HPC segment. And after that, we're going to have a quick review of what is a DPC++ and what kind of features we are supported for C++ or OpenP for the Xe accelerator. And then we are going through a couple of simple examples to give you some sort of intuition and what's happening based on the compiler and the runtime library, how you get some performance tips to get a better performance. One thing I want to call out about SMD parallelism, because in Intel's CPU and the GPU, we both have SMD engine inside the hardware. So there are some things I want to call out for you to aware of the difference between the Intel's CPU, GPU hardware versus some other vendors' GPU, for example. And the last part, I will show you some of the compilation flow and the runtime architecture. So you know roughly the high-level architecture of the compiler and the runtime we are building, what is more looks like based on the LVM infrastructure. Okay. So with some kind of a summary and a preliminary performance improvement we have done recently. Okay. Feel free to jump in if you have any questions. Okay. All right. If you look at the big picture of all the HPC applications, the AI application, and the framework people have been building in the past 10 or 5 years, especially when the AI field getting more booming up, right? So if you look at the applications, people have the HPC applications written in the C++ Fortran, and a lot of them, since you guys, all the HPC customers have been well optimized those applications over the years. There's a lot of work has been done by the national lab, U.S. national labs like Oak Ridge Lab, Livermore Lawrence Lab, Argonne National Lab. They have been building those COCOs, Rogers high-level framework, which is provides you a nice C++ interface. On the whole of those interface, C++ interface, then they build the number of the backend based on the CUDA, based on the OpenP, or based on the other sort of low-level or stacks people can provide. So all those stuff is going to boil down to the direct programming and the API-based programming, right? So direct programming including those languages. And for Intel, we are trying to add this new language. I will show you more information later. Plus the original OpenP C++, OpenP Fortran, and Python, Julia, all those script language. Beyond all those new language and the new compiler we are building on top of this, the LVM, our strategy is always aligned with the LVM, the top of the trunk. So we can leverage the community's work for all the new features, new improvement from the LVM infra and code base. Okay. And besides the language and the compiler support, we also have a set of the library provided by Intel across all the areas. For example, the MKL, DNA library, TBB library, OpenVINO, Parallel STL, MPI, and so on. So users can also use all those libraries if you like to get a better performance on the Intel, the GPU, and the CPU hardware, or even FPGA. Some library you can use for FPGA. So overall, we are trying to build this unified sort of a software stack, make sure we provide an easy way or some more effective way for the users when you develop your HPC or AI application, you can target the CPU, GPU, Xe accelerator, and the FPGA, device for delivered or provided by Intel. Okay, so this is the sort of the really high-level landscape of the Intel, the software toolchain, how the software toolchain can be leveraged by the HPC application and framework work. Okay. So the next, let's jump into why we're adding this new language. So a lot of people say the feedback we got, we have learned OpenP, CUDA, OpenCL, TBB, Parallel STL, a whole bunch of language. Why do we need another language, right? So without, let you see more information, you may say why, right? Okay, so let's take a quick look. What is the difference between those languages? With the CUDA, right, you write your own kernel. Then in the host code, you do those memory allocation, you're managing the manager the API to get a USN. Then you do the CUDA mem copy to the device, copy back from device to host. Then you launch your kernel. There's a whole set of things the user can do, which is pretty neat for the NVIDIA GPU. People get a nice performance out of that. But if you look at the OpenP is most of the users use OpenP. They start with a sequential C++ or Fortran code. They just put in the pragma with some sort of the source code modification, so they can say, for example, this one you just put the simple pragma. The compiler will generate the code for the offloading to the different GPU, NVIDIA GPU, Intel GPU, or different devices, right? So then let's look at the feedback we got from users. OpenP is a pragma or directive-based language, right? A lot of C++ programmers, they are not the fan of using pragmas. We got quite a bit of feedback from our users. So then we look at everything, look at all the standards people has been working on. One of the things pop up is the SQL from the Kronos group, the SQL language from the Kronos group. Then that was designed for the C++ user to write the C++ code to enable heterogeneous computing. We thought that language is pretty neat, and actually a lot of the C++ programmer probably it's more friendly to the C++ programmer, especially for those people who really like to use the modern C++ features like lambdas, template, accessor, all those kind of stuff, right? So, and also this is also aligned with the long-term strategy of the C++ standard committee, which we have been involved to push adding the heterogeneous computing functionality or features to the C++ standard, right? So with that as the vehicle to, exploring this path. So basically we took the SQL language, added a whole bunch of the extensions to the SQL. For Intel's product, we called it data parallel C++ as a sort of product name. From eventually, we hope in the long run, most of the features from DPC++ SQL will be part of the C++ standard. Intel has been working with the community and also working with the C++ standard committee, try to push forward on this direction. Okay. So, all right. So this is you can see there's a difference, and the feedback we got from users is DPC++ from C++ program point of view, it's more like a high-level construct, and it's a single source, same as OpenP. You don't have to write a separate kernel. Everything is embedded into a single source. You just use a lambda. Your kernel is part of your host code. You just use a lambda syntax to represent that. And also there's a set of other advantages. You will see the component of the SQL languages plus extension we have, what is part of this language, right? So, and before I show you all the features of the DPC++, the basic SQL execution model is based on the ND range model. Essentially, it's very similar to the CUDA's, the 3D threading model and the OpenCL's and your ND range work item, work group model. So essentially, the SQL Kronos group they started like leveraging OpenCL concept. That's why in the current SQL spec, they use the work group, work item as the basic terminology. But overall, it's pretty straightforward for people to understand the ND range in terms of the partition your data for the multiple threads or multiple execution units to execute them in concurrently. So basically, this is a simple ND range model with 2D. Then you have global size called 8x4. Then you can define your local size 4x2, which means then in that sense, you actually have two work groups. Each work group is going to take the 4x2 work item to work on. So in terms of mapping this model to the hardware, essentially you can say each work group you can map to the single thread, right? Each thread takes the 4x2 work item to work on. So basically, this mapping is, to me, is reasonably straightforward for the people to understand, especially for the people working on the data parallel application. Okay. All right, let's look at the the component of the DPC++ and the SQL language. So basically, they have this buffer. The buffer essentially, if you look at, if you use the OpenP, you know, when you use OpenP, in order to do the data transfer, you need to add to the map class, right? So you can create the device memory corresponding to your host memory and to do the computation on the device. So buffer essentially it's a way for the user to specify how the memory you want to create on the device. Then the buffer on the whole, the compiler runtime will generate the code to do the same as the map class, similar to the map class, generate the code to perform the data movement. Okay. Then as an Intel extension, we added this USM, and this feature is part of the current SQL 2020, which is already announced today, ratified today by the Corners Standard Committee. So the USM from the DPC++ is already part of the SQL, which is definitely our strategy to push those DPC++ features to be part of the SQL standard. And of course, the SQL language provides the scheduler, data parallel, task level parallel, low-level interpretability. Basically, in the SQL language, you can use the program object to load the OpenCL kernel or CUDA kernel and launch those kernel on the device as well. So it provides a certain level of low-level interpretability. Of course, there's the device management, right? Since you are doing the heterogeneous computing, you need how to manage your device. Besides that, there's a number of things like error handling and the building function. It provides a really rich set of the math operations. And for Intel, we actually added Intel's DPC++ compiler and runtime. We added those what we call the device runtime library to support the STD complex type, all those stuff, which is not originally wasn't part of the SQL spec. And of course, the language, SQL language has a vector type, scalar type, vector type, has those WSO support. And for this one, we have been thinking about working with the C++ standard committee because the C++ 23 will have this new feature called the C++ SMD templates, right? Which is driven by one of the European research institute and the university to be part of the C++ standard. And also there's a set of the device-specific extensions to enable user to get a better performance. So roughly, this is a high-level summary of those features. It's part of the DPC++, and besides the unified shared memory and device runtime and some set of the features, I can mention more in other forum. But overall, this language has been getting attractions from the users, from the C++ user community. Okay. So let's take a simple example. This example uses the buffer. Actually, if you use a unified shared memory or use a C++ 17 feature, which we extended that to as part of the beta 07 public release, is going to be launched, I think launched last week. A lot of syntax can be really simplified without getting those too much the C++ and make it much simpler. For example, actually we have the constructor combined the submit and the parallel for construct. You can just use a q.parallel for. So with a unified shared memory. So, but with this, this is aligned. Currently, this syntax we are inherited from the SQL language standard. Basically, user create your own buffer, then you submit this command to the queue, and this command including the launch kernels, which is doing the vector add operations. All those buffer get access, read write those operations. Essentially, let the compiler and the runtime to generate the create the memory on the device to do the and also to do the data movement from the device to the from the host to the device and the device back to the host. So basically, all you need to do is declare those buffers, use this get access, define those property read and write. So that on the whole, the compiler and the runtime will take care of actual low-level API, generate the code to do the data transfer for you. Okay. Hopefully, this is a very simple example to show you roughly looks like the SQL language and the DPC++ looks like. Okay. All right. Any questions so far? If not, we can move to the second part about the C++ OpenP part. And as everyone already knows, since OpenP 4.0 specification, we added a whole bunch of the constructs to support the accelerator or core processor and the devices for the heterogeneous computing, right? And also, since then, OpenP has been user space has been extended to the many beyond just high performance computing. There's a lot of domain and area like a medical imaging and the signal processor and autonomous driving. Those people have explored the usage in those different areas, which is a good sign for the building up or improve the ecosystem of the OpenP language. Okay. So if you look at the OpenP model, it's very similar to the DPC++ I mentioned. Basically, you have the host code, you transfer data to the device, create a memory on the device, transfer data to the device, copy the data from the device to the host, right? So there's a map clause, or user declared target, the compiler will take care of that. So on the whole, basically, OpenP offloading model also supports synchronized offloading, asynchronous offloading. So we are supporting those in our compiler, which is aligned with the LLVM community's OpenP work as well. So basically, we both support the synchronized offloading and asynchronous offloading for the users to fully leverage the system resource. Okay. So once we talk about the device or accelerator, we know not all the features in the OpenP, the core OpenP may not be, supported for the device due to some hardware limitations. As everyone knows, there's no OS operating system on the device, right? There's no scheduling in general on the device. So basically, all the thread launching, kernel launches from the host side, right? Even the number of vendors, NVIDIA, Intel, we have been looking at the dynamic parallelism, but so far, if you use a dynamic parallelism, functionally it works, but the performance is not really great because there's so many. You really want a full machine to be running at a high level, really have a high degree of the parallelism, right? So adding those scheduling, actually, some part of them, you have to serialize them, actually slow down the computation. So there is a pros cons for but at this point, most of the GPU, basically, we are fully enabled the high degree of the parallelism on the GPU. That's our first level of the goals, right? So with that, so basically all the OpenP offloading construct is part of our subset for the accelerator, XE accelerator, which is aligned with the community, LLVM community, and also other vendors have been doing. We try to sync up with all the vendors like IBM, NVIDIA team at a language standard committee to say what is the most a common set of the subset we should, of OpenP subset we should enable for the sub-device. We are pretty aligned on those subsets. So basically those subset definition is based on our HPC application users feedback, in-house application people, all the constructs that have been used, and also, the spec HPG working group from spec committee, right? They have a spec accelerator OpenP. Also, there's a spec HPC 2020. So we look at all the construct that has been used in those applications, try to make sure we are aligned with the community, and also make sure all the applications, construct used by all those applications has been supported by Intel's compiler and the runtime. So that's essentially three set of the sources. So we try to define this subset and to align with the other vendors and the community. Okay. And of course, besides the language construct, there's a set of the runtime. You don't need you don't need to read the fine print on the slide. Basically, this is just for your reference to know what kind of the runtime APIs we offer for the user to use to do the heterogeneous computing on the device. What kind of a runtime library interface we support on the device for you to query some information for the performance tuning. And in the OpenP 5.1, we don't have this global barrier concept yet for the machine-wide synchronization. And that's why I marked those two global barrier as Intel extension at this point. But in the long run, giving the feedback from users, we may propose this to the language standard committee, propose to the OpenP language standard committee for the 6.0 time frame to add a global synchronization, or you can call it machine-wide synchronization. And because we got requests from quite a bit HPC users that they need this feature. Okay. All right. So next thing is, since after we define the subset, then we need to understand how to map to those OpenP concepts to the, for example, to the Xe GPU hardware, right? So basically, if you look at the program model, there's a standard-based parallel program model, language and models, right? So OpenP is we have from the OpenP standard committee. OpenCL is from the Corners standard committee. And DPC++ it's based on the SQL Corners SQL standard, right? So then there is a vendor-specific the model from the NVIDIA. They have this CUDA model, which is a really good model for the NVIDIA GPU. And if you look at the cross, and there's a lot of similarity in terms of map to the hardware. So basically, OpenP Teams concept essentially can map to the OpenCL's work group and the DPC++ work group. And the thread is going to map to the subgroup. Essentially, it's a chunk of the iteration work item. If you look at loop iteration, it's a chunk of iterations. You want to enable that for the next level of the SMD level of the parallelism. So then on the NVIDIA, you can actually thread can be go to the thread that can go to the wrapper. Then inside the wrapper, you can actually each single work item can invoke with a single SMT thread, right? So that's roughly the mapping. But for there's a sort of different mapping given the NVIDIA hardware doesn't have explicit SMD support. They have this SMT is slightly different. So there's a different mapping. People think, they may only have two levels, thread block and thread, right? Because the SMT essentially becomes a thread. So there's a different mapping, a different thinking. But this model mapping, we try to see if you really want to write a portable application across all the architecture, this is a sort of level of thinking you can have to do the mapping between the different program model to the different hardware. Okay. So this model, essentially, if you look at the Xe GPU hardware we are going to offering, is OpenP Teams going to map to the thread group, and the thread going to map to the EU thread, hardware thread, then SMD map to the SMD lane. That's the sort of the mapping you can have. Okay. Of course, with those things, as I mentioned, we do support all those constructs, the SMD at a different level, and all the synchronization, global synchronization across the teams as the Intel's extension. Okay. All right, let's quickly take this simple Jacobi solver workload. This is basically the try to solve the linear equation AX equal to B. Then in order to do the transformation effectively, people actually did some transformation, low triangular, up triangular, and the diagnostic matrix, right? So with that transformation, basically the final equation x underscore nu equal to this mass of those set of this formula is implemented inside the code. So basically, the original implementation from one of our users for this simple workload, they just use a two offloading construct because they want to split the reduction into the separately, the first loop doesn't have doesn't need to worry about the synchronization or the stuff. But with then of course they create the data structure on the device, right? And user enter data, exit, copy the data back. So with this one, the simple tuning we do is we can merge two offloading constructs, just use the reduction on the compiler will take off that. This is one simple tuning. The second one is, if you look at the previous example, there's a simple type I is not equal to j, which is deal with the diagnostic the element, right? This means you have a branch inside your offload region. On the GPU, for the if you have a branch divergence, actually there's a performance penalty, right? So basically, we create get rid of that branch condition, create two small loops inside the offload region. That actually gives you a small performance gain by avoid branch divergence. And also merging the two offload region into a single one actually reduce some offload overhead, give you around 20% performance gain. This is just a simple example. I just try to show you there's a number of tuning user can do to get a better, slightly better, some 20% or 25% performance gain with simple tuning. Okay. And beyond that, for OpenP offloading, we also support this unified shared memory. Essentially, you can use this allocator when you use put this program in the memory allocation target will give you the unified shared memory, and you don't need to do the mapping across data map from the host to device back to host. Essentially, this is a unified shared memory you can use among the CPU and the device. Okay. We do support this in our One API Beta 7 release, which is officially launched last week. And also, since we are supporting the DPC++, and also there's a lot of existing OpenP applications, right? So the people, user keep asking, oh, if I want in my OpenP code, I want to parallelize more code by starting using DPC++, is that supported? The answer is yes. So basically, in the beta 07, we started support OpenP DPC++ composability. Basically, inside the OpenP code, you can incrementally adding the using the DPC++ code. And for example, in this case, the parallel sections invoke two function. One function use OpenP, another function use the DPC++, right? So in this way, you can incrementally adding the DPC++ code to your OpenP offload, the OpenP code as well, which provides some easy transition if some people really want to use the C++ syntax instead of the Pragma. Okay. Okay, the SMD parallelism I already talked about. There's a lot of things like a uniform, varying linear. Those things really has a big performance impact on the performance. Basically, if the compiler knows the memory access is linear, we can generate the unit stride load store instead of get a scatter, right? If we know it's a uniform, then we can actually use a scalar load store instead of using vector load store to reduce register pressure and so on our axis. So those information based on, we do enable all those analyzing and tuning and based on the OpenP for OpenP Pragma SMD to enable to get a better performance on the Intel's both CPU and the GPU. Okay. So then one thing I called before is we want to make sure we leverage, try to avoid the branch divergence on the SMD hardware, right? So this is not just an issue, not just on the SMD hardware. If you look at the NVIDIA SMT hardware, SIMT hardware, whenever they have a branch divergence, they also serialize the branch. So it's the same issue for SMD and SMT. So basically, it's just for the people to aware of there is a, if you can avoid the branch divergence, you actually can get some performance gains. Okay. All right. So next couple of slides, I will show you quickly the high-level architecture of the compiler to compilation flow. Basically, so the key message is that we try to leveraging the LLVM infrastructure to build the ahead of time combination and the jet combination as well. And the communication between the front end and the optimize the middle end to our back end is we are using the SPIR-V. Okay. So of course to build the fat binary. So you can look at this flow to understand the details. I don't need to read through those flows. And of course, for the jet combination with the fat binary, that we for the different devices, we are going to invoke a different backend to do the jet combination, then to generate the executable to running on the different device or hardware. Okay. And another thing is we're also working with the community, try to, for example, there's an OpenP offloading runtime API library, right? So we have been, Intel has been very actively working with the community, you know, Johannes, IBM, and NVIDIA. There's a lot of people involved. We try to make sure we have a nice design and all what we need to add different plugins for the different device. This has been paid off based on this design. We had worked with the community for over the years. So as long as you want to enable a new device, you can add your new plugin. Then you can target that plugin to your different low-level, you know, GPU driver or, you know, device driver to make it work with a very short amount of the time. Okay. All right. So we have it down and performance tuning for spec ICC OpenP on the Intel's. For example, GPU in the past 6 months, we have been making steady improvement over the 6 months. We have been improved from the day from the day we start tuning, and by tuning different scheduling mapping, we got about like overall we got about 25% performance improvement. We're going to continue to on this path to improve this as much as we can. Okay. So then the key message is. Make sure user understand there is no free lunch for any parallel programming and heterogeneous computing, right? So you really need to understand where is part of the code that you really can, if you do the offloading or use the heterogeneous computing, you can pay off the most, right? And also using the practice you had, same as the practice you had on the CPU or other GPU device, a lot of optimization tuning tips are really similar. So in that sense, a lot of the practice you have done before, you can carry it over to do for this new Xe accelerator and the future Intel's CPU as well. With that, I think that's all I have for today. Then I put some more information for you to download those tool chain Intel has been building and to to try that out. We're really in the position to help you to get your application running fast, and all your feedback for us is also going to help us to build the best software and hardware for you to get the performance benefit for your application. It's a mutual win-win situation today for both of Intel and the industry.
Perfect. Thank you.